In this lesson, we're going to continue our discussion of linear momentum by discussing collisions, specifically elastic, inelastic, and completely inelastic collisions and explosions. And this will enable you to solve problems using these that involve these type of collisions. So remember that momentum is conserved in an isolated system. So when objects in an isolated system collide, momentum is always conserved because the forces acting between the objects in that system are internal forces. And sometimes kinetic energy is also conserved in addition to momentum, and sometimes it's not. So just be careful not to get those two things confused. Momentum is always conserved in an isolated system, and sometimes kinetic energy is, and sometimes it isn't. Now we can classify collisions based on whether kinetic energy is conserved in addition to linear momentum. So remember, this is our statement of the law of conservation of linear momentum. In an isolated system, the sum of all the initial momenta is equal to the sum of all the final momenta. In an elastic collision, kinetic energy is also conserved. So the initial kinetic energy is equal to the final kinetic energy. So for example, let's say we had a particle moving to the right at 2 meters per second and one moving to the left at 3 meters per second. Let's take a look at a simulation to see what might happen. This simulation is from PhET, and I'll put the URL in the video. What we see here is two particles of identical mass 1 kilogram. This one, when I press play, is going to start moving to the right at 2 meters per second, and this one to the left at 3 meters per second. Let's just step forward a couple frames so we see what's going on there. And you can see that the momentum of each is at the bottom here as well. Now imagine that you were standing on this particle and watching what was happening. Although you're moving at 2 meters per second and the other is moving at 3 meters per second, it would look to you like this particle was moving to you at 5 meters per second. And the same would be true if you were standing on this particle and looking at the other. So their relative speed, or their speed of approach, is 5 meters per second. Now, when they collide and they move apart from each other, now you can see that they're moving apart from each other. They've each taken on new speeds. In fact, their speeds have swapped. This one's now moving at 3 meters per second and this at 2 meters per second. But the speed of separation is again 5 meters per second. And that's going to happen in perfectly elastic head-on collisions. In fact, even if I change the mass of one of them, let's make this one bigger, and I do the same thing. Again, they're going to have a speed of approach of 5 meters per second. Now they haven't swapped their speeds, but you can see that the speed at which they are separating is again 4.67 plus 0.33 meters per second, again 5 meters per second. So the speed of approach and the speed of separation are the same when there is a perfectly elastic collision. So again, in a special case where these two particles are of equal mass, they will swap velocities, meaning this one will now take on 2 meters per second to the right as its velocity, and this one will take on 3 meters per second to the left as its velocity. And you can show that that has to be true in order for both of these conditions to be met, for the momentum of the whole system to stay the same, and for the kinetic energy of the whole system to stay the same. But even if they're not the same mass, whenever you have a perfectly elastic head-on collision, the speed of approach and the speed of separation are going to be equal. Now, although particles on an atomic level might be considered to be undergoing perfectly elastic collisions, nothing bigger than that, nothing macroscopic really does, essentially, although billiard balls are a pretty good approximation. So we need to talk about inelastic collisions. And in an inelastic collision, the kinetic energy is not being conserved because some of it's getting converted into some other form. Momentum, of course, is still conserved if we're talking about an isolated system, and that's easy to get confused again. Kinetic energy is not being conserved, but momentum is still being conserved in an isolated system. In a completely inelastic collision, the colliding objects stick together. So let's take a look at that on the simulation now. Now in this example, I've got two equal mass particles which have equal and opposite velocities, and therefore they have equal and opposite momenta. This one has a momentum of 2 kilogram meters per second, and it's going to be to the right, and this one 2 kilogram meters per second to the left. The system of the two particles, therefore, has an initial momentum of 0, and this is an isolated system, so the total momentum is going to remain 0. In this case, I've changed it so the elasticity is registering here at 0%. It's a completely inelastic collision. That means that when they collide, they're going to stick together. Let's watch what happens. They collide and they stick together, and the only way for that to happen and maintain a total momentum of 0 is for the whole system to come to rest, because they had equal and opposite momenta to start. Now, if I were to change the mass, let's say, of one of them, then they do not have an initial momentum of 0. Let's watch that again. The total momentum is going to be leftwards, because this one has a greater leftwards momentum than this has a rightwards momentum. But the velocity to the left here is less than the initial velocity of 2 was at the start. Notice that the total momentum here is equal to -2 kilogram meters per second, and that's the same as the sum of these two as well. So in a completely inelastic collision, the two particles stick together. A variation on this idea of an inelastic collision is an explosion. In an explosion, the kinetic energy of the system actually increases, but once again, if the system is isolated, momentum is still conserved. So imagine you had a frictionless surface with two boxes with a compressed spring in between them, and then you let that spring uncoil, you let it spring. The total momentum of the system would be conserved, and the kinetic energy would increase. Here there's no kinetic energy, and now the kinetic energy is larger. Remember, kinetic energy is a scalar, momentum is a vector. A more familiar example might be fireworks. If you watch fireworks going in the sky and they're following a parabolic trajectory as a projectile, and then they explode, the pieces of the fireworks will go off in all sorts of different directions, but the sum total momentum of all these pieces is actually still conserved and still following this trajectory. And we can think about that even more carefully if we consider the idea of the center of mass. Now, the center of mass of a system is just the mass-weighted average of the position of all the particles, or the average of the position of all the particles in the system weighted by mass. Imagine you have a small particle here and a more massive particle here. The center of mass of these two particles is going to be pulled to the right by this more massive particle. So the center of mass, for example, might be there, depending on the masses. Now, from the outside, we can treat systems as if all of their mass is actually concentrated at the location of the center of mass. And in fact, that's what we've been doing when we've been drawing free body diagrams and reducing things to a single point. We've been treating them as if all of the mass was at a single point. And we'll do that again when we talk about gravitation. We will imagine the planets are just mass concentrated at their center. Now, as long as a system is isolated, the velocity of the system's center of mass is going to remain constant, even though parts of the system are colliding, because all of those collisions just result in internal forces. And as we saw earlier, the internal forces, because they are Newton's third law pairs, do not cause the acceleration of the overall center of mass. Here's our example from the inelastic collision again, but now the center of mass is marked. And notice that the center of mass of the whole system is closer to the more massive particle than to the less massive particle. If I press play, we'll see that that center of mass starts moving to the left as the more massive particle starts moving to the left. Now, when they collide, it just keeps on going to the left. And if we watch that again, you can see that the center of mass's velocity does not change at all. One way of thinking about this is imagine that these two particles were, let's say, gas particles in a balloon. The fact that they collide would not change the movement of the overall balloon. Or if they were particles in your body that are colliding, they're not going to make you lurch forwards or backwards. And you could see that as well. If we made this an elastic collision, that doesn't change. The velocity of the center of mass still remains constant, even though it is no longer within either of the particles. Let's use this table to summarize now. So momentum is always conserved, whether we are talking about elastic or inelastic collisions or explosions. Kinetic energy is only conserved in elastic collisions, but it is not conserved in inelastic collisions or explosions. One last thing to note, if you take a look at our formulas for momentum and for kinetic energy, we can derive one more. If I square both sides of the formula here on the left for momentum, and then I divide both sides by 2m, then I get m squared times v squared over 2m, or 1/2 mv squared. So p squared, momentum squared, over 2 times the mass is equal to our formula for kinetic energy. In other words, we now have a new formula for kinetic energy, p squared over 2m, and that allows us to, for example, solve for kinetic energy without having to fuss about the velocity because it's not in the equation here. Okay, so that's an introduction to the different types of collision.